Hello friends, today we will discuss and derive the third boundary condition for electromagnetics, that is dn1 equals to dn2 and dn1 minus dn2 is equals to sigma. So let us discuss and derive. Now first, what is this D? D I have discussed in my previous video lectures. D is the electric flux density. Electric flux density, okay, coulombs per meter square, okay. And the statement of this boundary condition is that the normal, I have mentioned dn, okay, the normal component of electric flux density D is continuous. It is continuous across any surface except at the surface which has surface charge density, okay, that is dn1 equals to dn2. The normal component. Now what is the meaning of normal component? Remember, in the last two boundary conditions we have talked about the tangential components. Now tangential component means if there is a surface, for example this, and if the components are parallel along this side, along left side, along right side, then these are the tangential components. Now if there are components which are normal, perpendicular to this boundary, it is known as the normal component, the perpendicular components, okay. The normal components of D is continuous, that is the component along one side is equal to the component along other side, except at the surface which has a surface charge density. Now if there is any surface which has surface charge density, then this boundary condition will be equal to the surface charge density, that is dn1 minus dn2 is equals to sigma, where sigma is the surface charge density, okay. So this is the statement. Now let us derive this derivation, this discussion, okay. Now consider a cylinder, okay. Now this is our cylindrical surface. Consider a cylinder. Why we are taking cylinder in this boundary condition? Because we are talking about the flux density, and flux will always pass through the area, okay. So it is coulombs per meter square. Now if we will cut this cylinder in between, okay, then from in between the shape will be again cylindrical, okay. So here it is the boundary, and this is our small amount of area, okay, the cap area. Now this boundary has divided this cylinder into two portions, medium 1 and medium 2. Medium 2 has characteristics epsilon 2, mu 2, sigma 2, and it has characteristics epsilon 1, mu 1, sigma 1, okay. Now fine. Now suppose the electric flux, the electric lines of force are adding to through this surface, and inserting, going into this surface, okay, entering into this surface, that is, because it is the second portion, we will write it as dn2. It is entering the surface normally, okay, and then it is leaving the surface, dn1, okay. The flux is entering the surface and the flux is leaving the surface through here, Okay, so this component I have written dn1, this component I have written dn2. Now we can derive this boundary condition with the help of Maxwell's first equation. Maxwell's first equation. Now what is Maxwell's first equation? Maxwell's first equation is integral of d dot ds equals to rho dv equals to q. Now what is rho dv? Rho dv is equals to q. I have already derived the Maxwell first equation and I will insert the link in the description. Okay, so d dot ds equals to rho dv equals to q. Okay, the first case, if there is no charge at the surface, that is q is equals to 0. Now if q is equals to 0, then this equation will become d dot ds equals to 0. Now suppose the suppression between these two flat surfaces, it is delta x from center to center. Okay, delta x from here to here, it is delta x. Okay, now we will expand this left hand side. Now we will take this surface, okay, so it is equals to integral of dn2, and suppose this direction is our, you can say this direction is our y-axis. Okay, j cap. Okay, this direction is our j cap axis. So dn2, so what is the direction of electric flux density? It is j cap. Okay, now dot product ds. Now what is ds? Okay, this is delta s. Now what is the direction of this cap? This is always outward. Outward means in this case it is along this direction. So it is minus of j cap. Okay, dn2 j cap delta s minus of j cap. Fine. Okay, plus now the flux is leaving through this surface, so it will be dn1 j cap. Now what is the direction of this cap? It is outward. It is always outward. Okay, so it is j cap equals to 0. Okay, dot. Now what is j cap dot minus j cap? Okay, j cap dot minus j cap, and it will become d minus dn2 delta s, and it will become dn1 delta s equals to 0. Okay, so it will become dn1 minus dn2 delta s equals to 0. Okay, but delta s cannot be 0. We have done if AB is equals to 0, either A is equals to 0 or B is equals to 0. Now delta S cannot be 0. It has some area. Okay, so what can be 0? That is dn1 minus dn2 is equals to 0, or dn1 equals to dn2. Okay, this is the first condition of the third boundary condition. That is, the normal component of D is continuous across any surface except at the surface of discontinuity. Okay, so integral of d dot ds equals to 0. What we have done, we just have put, that is we just have expanded this. Okay, d and 2 j cap dot d delta s minus j cap. Okay, after solving, because a dot b is equal to ab cos theta. Okay, in this case it is cos of minus, basically it is cos of 80 degree. Okay, cos of 80 degrees means -1. Okay, so after solving this, we will get minus dn2 delta s plus dn1 delta s, or dn1 minus dn2 delta s equals to 0. So this is the first condition of the third boundary condition. Now, if there is charge present, second case, in this case, if there is charge present, or you can say if it is a metallic surface, and if there is a charge, then integral of d dot ds equals to q. Now q is not 0 here, so just like expanding this relation to this relation, now right side will not be 0, okay, so we will get minus dn2 delta s plus dn1 delta s equals to q, okay, or dn1 minus dn2 delta s equals to q, or dn1 minus dn2 equals to q divided by delta s. Now what should be charge per unit area? It is sigma. So dn1 minus dn2. So it becomes discontinuous. Okay. That is the normal component of these discontinuous by an amount equal to the surface charge density. Discontinuous means that is dn1 is not equal to dn2. So this is all about the third boundary condition, that is related with the electric flux density. And if you have any doubt, please share in the comment section. Thank you.